Okay, so now we're going to look at the relationship between the solubility of a solute in a solvent and the temperature, all right, of the solution. So here we have a graph which shows you how the relationship between those two. On the y-axis, we have the solubility, and on the x-axis, we have the temperature. And as you can see, for the vast majority of the solutes, the solubility tend to increase as the temperature increases. So we can see in some cases where that's a very dramatic increase, as in the case of potassium nitrate, which is the curve here, colored black. Sodium nitrate, not as steep, but you can see again the trend. In the case of sodium bromide, it's a very slight increase as you go from 0 to 100 degrees, but you have a few substances where the solubility actually decreases as the temperature increases. So one example of that is sodium sulfate shown here. And here we have cerium sulfate, serum 3 sulfate, again showing that particular unusual decrease in solubility as the temperature increases. So as you can see, for most solutes, their solubility increase as the temperature increases. Okay, so that is basically what is said here. General trend for most solutes, but have of course the two examples I showed you before where they tend to buck that trend. Now we can exploit the solubility of different solutes to do what is known as fractional crystallization. So basically this is a way of basically separating two solutes in a mixture based on their differences in solubility in the same solute. So the example that is shown here is potassium nitrate and sodium chloride. Now, let's say we have a mixture of those two where the amount of potassium nitrate is 90 grams and the amount of sodium chloride is 10 grams, right? And they're both dissolved in 100 grams of water, all right? So you'll notice here that for potassium nitrate, the solubility of potassium nitrate at about 100 degrees Celsius, at about 60 degrees Celsius is 112 grams per 100 grams of water. But if you lower the temperature to down here, I'm not sure what temperature is represented down here, but you see that the solubility of potassium nitrate is reduced significantly. Now, in the case of sodium chloride in the same mixture, its solubility does not change much going from 0 to 100, right? So therefore, you would expect that at even 0 degrees, actually this is what the temperature here is, 0 degrees, all right? So even at 0 degrees, the solubility of sodium chloride is pretty much the same as it would be at, let's say, 60 degrees, all right? So basically, to achieve the separation of the potassium nitrate from this solution, what we do is that we dissolve these two in the mixture in 100 mils of water at 60 degrees. And then we cool the solution to 0 degrees, all right? Now, of course, the solubility of potassium nitrate will be reduced, which means that some of it will come out of solution, while the sodium chloride will remain in solution. So what was determined here was that 78 grams of the potassium nitrate will come out of the solution. And we can actually calculate that based on the fact that we started off with 90 grams of the potassium nitrate, and we know that at 0 degrees, the concentration is 12.1 grams. So therefore, the difference between the 90 and the 12.1 grams, which is shown here, will give you the mass of the potassium nitrate that will come out of solution. So therefore, you would have succeeded in separating 78 grams of potassium nitrate from a solution which contains 90 grams of potassium nitrate and 10 grams of sodium chloride. So we call this fractional crystallization, which is a very important separation technique that is used for purification of compounds from mixtures, as you can see in this example. Okay, so enough of that. Let's talk about another factor which affects solubility, and that is temperature. And as you can see here, we have a plot of the solubility on the y-axis versus temperature for oxygen gas in water, right? And as you can see clearly here, the difference is obvious when you compare to what we just discussed, because in the case of oxygen, like any other gas, the solubility decreases as the temperature increases, all right? And this is important, especially if you have concerns about the environment. As global warming progresses, the temperatures of our seas and rivers increases. That reduces the amount of oxygen in our aquatic environments, and therefore, as you can imagine, aquatic life can be affected as a result. All right. So that's basically what the relationship between the solubility and the temperature of a gas dissolved in water is. All right. So another relationship I want us to look at is the relationship between the pressure of a gas above the surface of the liquid or of the solution and the solubility. And the relationship here is described by Henry's law, which says that the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution, all right? And we can represent it by using this mathematical equation. C is equal to K times P, where C is the concentration of the gas in the liquid, and the P is the pressure of the gas above the liquid, right? Um, so K, of course, is a constant of proportionality, and that value is constant as long as the temperature is constant. So if the temperature changes, then the K value will change, right? And this is what is being demonstrated in this diagram here, right? So when the pressure is low for the gas above the surface of the liquid, the concentration of the gas in the liquid will be low. But if you increase the pressure of the gas above the liquid, then the concentration of the gas in the liquid will increase. All right, so that's basically what Henry's law is all about. Okay, so we're going to stop here. So the next couple of topics in this chapter, we'll be dealing with the colligative properties of solutions. All right. Okay, until next time.